Welcome, everybody, to the American Space Museum. I'm Mark Marquette, and we're so glad you're with us to Stay Curious today. A very special program. As you see, sitting beside me is Kevin Hoshstrassoer. Kevin, welcome to Stay Curious.
Well, thank you for the invitation.
Well, it's special because this is one of the gentlemen that knows everything, or a lot, let's say, about this engine behind us here. What is considered one of the best rocket engines ever made in the world, the Space Shuttle Main Engine, SSME. It's now called the RS-25 in the Artemis world. But Kevin, we're happy to have you here. You've got a beautiful model that he's made. What do y'all see this? A 3D model we're going to talk about. And we're going to get a little history lesson about the SSMEs. And from one of the horse's mouth, so to speak, one of the men that I guess helped pioneer it, to develop it.
Well, some of the development, but what I need to say is I'm humbled and honored to be here, first of all, because there are so many other smart Rocketdyne people in this area, even on your board, who are better suited to do this than I am.
Mm-hmm.
There's
well, you see how desperate we get sometimes.
Well, no,
Kevin.
Lee Solid is an icon in the SSME world.
Absolutely.
These are all my mentors. John Plowden, who knows more about this engine than ever. Eric Gardsey, Dan Hausman. Dan Hausman is one of the smartest people I know, and he's one of the actually people who really helped design and implement this. And whenever there was a problem, it's people like Dan Hausman and all these other people who I got to work with and who are much smarter than I am to do this. So again, I'm humbled to do this because there are so many folks who you could put in this chair.
Well, we're glad you're here. Hold that up in front of you there. What he's referring to is this beautiful 3D model of the Space Shuttle Main Engine, and we're going to go over that in a little bit of detail here in a minute. Built on your 3D printer at your home, huh?
Well, I actually had most of this contracted out, and
okay.
But I designed it. I've designed it. Of course,
hold it up. Let me show it.
Because I had access to the drawings of the Space Shuttle Main Engine through my career, and
who'd like to have this in their space cave, huh? Sitting on the coffee table.
Yeah.
Very lightweight.
Well, it's
I can tell, very professionally done, this 3D model there. That is really something.
That's what I did in my retirement.
Good. Well, we're going to talk to Kevin about this engine and how it has segued into the moon rocket, SLS. Of course, we're going to, as I ask you a little bit about where you grew up and so forth, we've got some pictures courtesy of Carlton Bailey. Thank you, Carlton. He put this triple header together there. Of course, the blue diamonds of those engines there. You're going to tell us that signature and how happy you were always to see that, I'm sure.
Well, we call those Mach cones.
Mach cones.
The official term for those.
M-A-C-H?
M-A-C-H.
Cones, okay. Well, I
Mach.
won't call them blue diamonds anymore, Marty. My way to say hi to Marty Winkle that worked on the launch process systems. I couldn't separate him and Kevin much as they're in here talking about what's going on. And sorry there, your name got misspelt there. It's S-S-E-R. And
there you go.
But we did our best. Thank you, Trekkie Techie there. But Kevin's so much more than that title there. We couldn't get everything in there. But hi, Marty. As you're writing down some of our friends' names there, say hello to everybody on our UCAC family microphone.
Hello, Mark and Kevin and everybody else.
Good. How do you know Kevin so well?
We were kind of, I guess, counterparts. He worked for Rocketdyne on the main engines, and I was main engine controller engineer for, back then was Rockwell International.
Mm-hmm.
So we were counterparts.
Great. Of course, we're proud of Marty working on as an electrical engineer on our lunar modules that we'll be celebrating the 54th anniversary of Apollo 11 here in a couple weeks. Time flies, doesn't it?
Oh, yeah, yeah.
And as well as the 12th anniversary of the last SSMEs operating on a shuttle's coming up here, too. So I don't want to make you feel old there, Kevin, but hard to hide the gray hair at our age.
Yeah.
But as I ask you, where'd you grow up?
Well, I grew up in Dayton, Ohio, and soon, just a little bit before I finished high school, I moved to Florida on my own and put myself through college at the University of Central Florida.
Excellent.
And upon graduation, I graduated college just in time, just before STS-2.
Mm-hmm.
And I came over here to the Space Center with a handful of resumes and walked around trying to see who would talk to me. And my dad worked at Vandenberg Air Force Base at the time, and I shipped him some. And I was not able to find a job, but my dad was able to get me an interview at Vandenberg. So I actually joined the space program and opened up the office for SRBs at Vandenberg Air Force Base. Worked a hydraulic APU system for USBI, the SRBs, and then transferred to Rockwell Space Division out there in 1983, and worked for Rockwell Space Division when we were trying to launch shuttles from Vandenberg Air Force Base. After a short time, I wrote software for the firing room, and after they finished that, my job was complete. The firing room software was complete, and since I had just finished writing the software for the C12 and the C3 consoles, the SSME consoles, I was actually offered a job to transfer from Space Division into the Rocketdyne Division by a mentor of mine, Vince Wheelock, who has become the unofficial historian for Rocketdyne. And so that's why I picked up so much information.
Vince Wheelock.
Yeah, another hero of the space program. And after Air Force decided they did not want to launch space shuttles anymore, I actually was invited to come to Florida by Eric Garzi and Lee Solid and John Plowden to become a part of the launch team here. And that's when I met Marty, worked avionics for a number of years. Then I transferred into the flow management, flow leadership, where I was the tail lead, where my job was to plan the requirements for a mission. So I followed basically one orbiter, the Discovery vehicle. And
These are just kind of...
Yeah, just even in between what engines we were going to use, what work needed to be on, what work we had to do on the engine before it was ready for flight, and do all the pre-ops for that, interface that with the other contractors on the site. And then I got an opportunity to join the safety and quality team at Rocketdyne. So I worked safety and quality for a number of years for Rocketdyne. And in the meantime, Rocketdyne had been merged into Boeing. So an opportunity came in the early 2000s to transition from a Boeing Rocketdyne job to safety and quality for Boeing's the site leadership. So I was represented safety and quality for all the Boeing and Heritage Rockwell Rocketdyne teams. And after a number of years, I became chief engineer for Boeing at the site.
Mm-hmm.
And in 2007, I became the program manager for the Florida space operations. Since Boeing was in Rockwell were the original equipment manufacturers for the orbiter, this team I worked with, were responsible for all the engineering on the orbiter. We still own the orbiter as original equipment manufacturers, and we would be responsible for make sure all the engineering done on the vehicle was per print and per drawing.
Mm-hmm.
And a year later, at Boeing, you always had to have two jobs.
Okay.
So I had a part-time job as the senior site executive for Boeing Florida operations, which represented all the Boeing contracts and personnel here at the Space Center at the time, which at the time was fairly large. But over time, Rocketdyne was sold to Pratt Whitney. The Delta 2, 3, and 4 folks were merged into ULA. And of course, at the end of the contracts, the shuttle came to an end. So did my career.
So did a lot of careers, but yeah, at one point, you from your notes, there's over 900 Boeing personnel.
Well, we had almost had that many engineers.
Engineers?
We had around 1,400 employees before all the divestitures.
What a career, folks. Now, when you were in Dayton, Ohio, there, you were close to Wright-Patterson Air Force Base, of course. And, of course, down the road was the Cincinnati Big Red machine, too, down there.
Yeah, and more importantly, just north of us was Wapakoneta, Ohio.
Yeah, right. And where Neil Armstrong grew up, in Findlay, Ohio, about 2 hours north of you, is where I grew up in there. Did you play with ST's Rockets or anything like that? Where did this come from, your affinity to be around rockets?
It's hard to pinpoint it, but I do remember my father got us up every morning for a space launch. And it was just kind of osmosis, but I just always kind of knew in the back of my head I wanted to be in the space business.
Now, how were you going to see a space launch back in the last century?
On TV.
Oh, gosh,
On TV, yeah. We didn't do
but I mean, of course, the crude ones we're talking about mostly then. And,
Yeah, I was fascinated by that, but I had to work hard to achieve the grades to get into engineering. And like I said, I always knew that I would somehow get into the space program.
That's neat. That's neat. I was crazy about astronauts and telescopes, but I did a wrong turn. I tell people, do not go into liberal arts. All right, because I wanted to be Woodward and Bernstein, the Watergate, and I went as a newspaper reporter. Go into engineering like this man, and part of it was, just the esoteric things going on there. Well, we're talking here with Ken Hoshstrassoer. He has had a great career involved with the Space Shuttle Main Engines. We got this picture of Carlton Bailey's here in our background where we were getting your fabulous bio there. Okay, and that is the cones, the
mock cones.
Mock cones. All right, I'll have to.
I'm going to start using the word blue diamonds. I like that too.
Oh well, no, don't change for me. That'd be horrible. But we're looking up here at the couple. There's Dan Hausman. Hi, Dan. He's been on our Stay Curious program. And one of your colleagues' mentors, too.
Mentors. Dan Hausman there's so many.
He is a very smart man, I know.
In fact, I think that's why I had to get out of Rocketdyne and into Boeing, because Rocketdyne had so many smart people. And it was very humiliating and humbling for me to always be the dumbest one in the room.
Well, what makes him smart? And here's Lee Solid. We want to give a shout out to Lee there. I mean, is it it's not their vast book knowledge, is it? Is it their...
Well, yes, it was.
Okay.
It was their vast book knowledge. And a lot of these people, they were a generation. They actually took part in the program before the shuttle started, so they knew more the development and how the engine worked. My experience from how the engine worked came from sitting with these people, sitting up and listening to everything they said. But Dan Hausman could digest and understand a problem, a systems problem. When you're in the rocket science business, it's just not one discipline. You have to understand many disciplines to get to the core of an issue, whether it doesn't have to be a catastrophic issue, but just a little funny data you see in an engine test. Dan and Eric Gardsey, Jim Chilton, the current, I think, technical leader out there for Rocketdyne right now is a gentleman named Bill Muddle. They were all able to sit there and just digest and pinpoint a problem. John Plowden used to always tell us, never turn your back on a rocket motor.
Ooh,
because he would know it goes from really good to really bad in just a couple milliseconds.
And then you said something earlier in our pre-production meeting here. The hardware talks to you.
That's another thing that John Plowden and Dan Hausman would always tell us. The hardware is always talking to you, so you got to look at the data. When we would do engine tests, we would get reams and reams, and it would take us not hours, it would take us weeks to go through the data and look for anything off nominal. And sure enough, you'd see data, but you say, this data is within limits, but it's just not to where it was yesterday, or last time we tested it. And it wasn't, it doesn't match really precisely. So pay attention to it. And so we learned, because of our great mentors we had at Rocketdyne, we learned to pay attention to those details and don't ever let a piece of data, not be answered.
Kevin, something popped into my mind that one of our old unmanned rocket guys, Murphy Wardman, who's 91, always said that when we got a rocket launching the Convair General Dynamics Atlas rocket in the 60s, he said when we got a clean machine back from the factory, the launch we had problems with. When it came back to the machine from the factory and we had to massage some pieces and parts and play with it a little bit, the launch went flawless. I mean, is that a Murphy's Law or something of the rocket world?
It's an axiom and it's a fact in the rocket business that when they come to the launch site, some assembly is required.
Okay.
They come out of the they do a good job, but they have specs and they manufacture it properly, but there was some assembly required when we got here, and we would have to do some inspections and I think when Marty and I used to work together, our job was to go out there and reroute the harnesses, and we'd do a lot of extensive testing before it got here.
Well, interesting. Marty, you're right, a lot of viewers that are watching this wonderful program. I'm excited to hear what Kevin's got to say. He's already enlightened us so much already. Marty, what's on your mind there, buddy?
Kevin, you talked about reading the data. And one of the people that I've always been impressed by, he worked for Rockwell, then he went to Rocketdyne, was Dick Carlson. And he used to line the walls up after a launch and just, back then it was strip chart recording. And he'd analyze every engine, every measurement. It would take him a few days to do that. You want to comment on Dick?
Dick Carlson was a hero of the Space Shuttle Main Engine. He actually was an encyclopedia for us. He actually worked F1. He was one of the folks who worked the F1 engine.
F1 engines on the Saturn V rocket. I got to interject some.
Yeah, so he was one of our heroes, and he was, I want to say, like a guru. He would sit. He had his own little cubicle, and it was stacked. In those days, everything came out on computer paper, and all the data was just full of data. And we would see stacks. I mean, I used to go into his cubicle and sit on the stacks to talk with him.
Carlson, right?
Dick Carlson.
Dick Carlson.
He's a local gentleman, and he was one of those people that I described, that people who were just so smart. But Dick used to do that. Remember, we used to go to the second floor of the LCC, and we'd have these strip charts, and we would go back to the hallway, and we would just roll them out. And these strip charts were literally 40 feet long.
Wow.
And we would go down millisecond by millisecond and look at the data. And Dick would look, and I wasn't very knowledgeable at the time. I was still up and coming in those days. But I used to watch Dick Carlson and some of these other gentlemen that I've talked about, and they would go and say, "Oh, what's wrong with this?" And my attitude at the time was, "It's a thin spec. Let's move on." Oh, no. This is something to look at. And it gets back to, make sure you listen to the hardware because it's talking to you. And Dick used to do that. And these people I talked about, they're such heroes of mine. Dan Hausman hadn't moved down here to Florida yet, but Canoga Park was full of a number of people who used to be able to do the same thing. But Dick Carlson, he had all the manuals from the Apollo program, and he when you went to him, he would not only tell you what the problem was, he'd tell you how it was caused, what to do about it. And he was very involved in what we called the pneumatic control assembly. It's such a minor part, I don't have it modeled here, but that would control all the purges. And he designed and modified that PCA to do so many things that it wasn't intended to do, just by his imagination and his knowledge of how the engine worked as a system.
Mm-hmm. He would explain these things as matter of fact, like it's just common knowledge. It was far from common knowledge.
Oh.
And that's why it was good to get out of Rocketdyne, because I hated being the dumbest guy in the room all the time.
Talking about Dick Carlson, one of the rocket people there that built this incredible engine. We're seeing our green screen here in a test at the facility in Stennis, and Kevin's going to talk about that in a little bit. I'm going to have some slides that I'm going to breeze through there, everybody out there a little bit, because Dan and I met a couple of weeks ago and arranged this interview, and I've had a chance to get to know him a little bit. We did want to talk about Lee Solid there. I talked to Lee on the phone. He's doing well. He brags about this engine. The SSME is the highest performance engine ever built. He said the specific impulse.
Yes.
Nobody else has built an engine that has this powerful specific impulse. He said, Mark, think about it like miles per hour. There are bigger engines, he said, they're not as efficient. The pounds per thrust, pounds of thrust per pounds of fluid flow.
Exactly.
Is the secret there.
Pounds of thrust versus over is a ratio over the pounds per second. So when you do the math, the pounds cancel out, and the number that's the actual answer of that ratio comes out as seconds.
All
so
right.
that's how you judge an engine's efficiency and its power.
Well, he said he's impressed at Elon Musk's engines. Those Merlins have been used so efficiently, and particularly flying that one 16 times the other night. But he said that one of the SSME engines flew 14 times. But he was an architect, of course, of the F1 engines of the Saturn V rocket. But he's so proud to have a part of this reusable, folks, engine, which you told me there was about 40 of them in inventory.
Well, originally manufactured over the whole course of the program, 46 SSMEs were built.
Okay.
And at the end of the shuttle program, 16 still existed. over time, a lot of those, we're going to talk about engine testing. We spent a lot of time engine testing, so a lot of them were consumed. Their life limit was expired through engine testing. A few of them were used to test to destruction in some tests. Some were in museums, but after the shuttle program ended, we had 16 left, and of course 4 have gone with the Artemis 1, so that leaves us with 12 engines right now.
All right, and those 4 of those will be used on the Artemis 2 in November 2024, folks. So a year from now, and then of course we hope 4 of them will be used to take us to the moon, to land. They're gonna pass by the moon on Artemis 2 in there, but there's a beautiful test stand there. Okay, the mock cone there below it. I always love the looking at right around the rim and all this happening around there. And you break it down in milliseconds, there's quite a lot going on there, obviously. But let's go to just about this engine, some of the dimensions. 14 feet tall, 7.5 feet wide. The data here I'm going to read, Kevin, what sticks out to you there that we space geeks should pay attention to this chart there?
The number of the efficiency of the engine with 452 seconds of impulse was really what made it special, because a very efficient engine. But this engine, I don't see it there, but you can't forget that it's not only reusable, it's throttleable.
Yeah.
Try to say that. So you can adjust it, and we'll talk about that here, I think, a little bit. But it's a high pressure engine. That's what NASA wanted for the. So it got a high pressure engine. It is a fuel rich engine, which maybe we'll talk about later too. It's the kind of engine, and the propellants are hydrogen and oxygen, and that's why when you see that flame, it's clear. But when this thing just turns hydrogen and oxygen into some water.
Hydrogen minus 423 degrees Fahrenheit, below zero, by the way. Of course, 3 SSMEs every flight, produced over 37 million pounds of horsepower, which they say is the equivalent of 13 Hoover dams. I don't know how long those Hoover dams are running there. But and the fuel pump that we're going to see, the turbo pump generated 70,000 horsepower, which was significant to its output there. So a few little facts there to whet your appetite. Just quickly, from post-flight inspection to get it to the next launch is this whole chain of things that I'm sure you were very involved in.
This was part of my job for a little while. I would follow a flow like this around for Discovery and coordinate all the planning and requirements to get 3 engines ready for the next mission, and then we would just leapfrog the different vehicles. But of course, everyone likes to point out when this space shuttle was first designed that this flow was going to take 11 days.
Right, yes.
But over time, on the space program, with the human-rated space program, whenever there was an issue, it required action. It required testing, inspections, and over time, this list kept growing. And once you add a test, once you add an inspection, it's very difficult and probably not smart to try to delete it. So each test that we incorporated, so over time, this became more and more a longer list of things to do. So I think it was back in the early 90s, we actually took a proposal to NASA. Instead of doing all this work that we had to do in between turnarounds for engines on the vehicle, we found out it was actually quicker to take the 3 engines out and work on them offline. We had a nice engine shop that we had developed there in the vehicle assembly building, and later a separate building by itself, and we would do all the testing out offline. And so when the vehicle came back, all the other systems could do their work, and just before they're ready to roll out, we would install the 3 engines, do a minimum of testing, but all 3 engines that we installed were ready for flight, checked out. All we had to do was do the interfaces, and that worked out really good. But we had to, as you can see this list, there was a lot of things to do. Whenever you did an inspection, if you broke a joint, opened a joint up, you had to verify that it wasn't leaking, so there's leak checks involved with every broken joint. And over time, we had some problems with some high-pressure oxidizer turbo pumps over the years, and so every time we saw a problem, or like we talked about when Dick Carlson or Eric Garza or Dan Hausman would find a problem, data problem, we'd say, well, let's take a look at that after mission. And we said, it's a good idea to look at it every time. And so we would do all those inspections and get it ready. So when it was installed, it was ready to fly.
That's so. Just the attention to detail, folks, is what made this the great engine reusable. Marty, where were you on this stair step of things in there?
After the engines were installed in the orbiter, we would do the testing for engine checkout and then get involved with the launch countdown.
Good, thank you. So we're going to bring your model in here, and don't be all these charts and so forth I'm giving to our stay curious friends out there, just sort of you all to digest a little bit. We're gonna go this. Marty might zoom in a little bit. Dan or Kevin, if you just put it right there. Yeah, Kevin.
Okay.
Kevin, you're doing an awesome job. I think everybody out there, I see Marty writing down a lot of people from around the world watching us here. I'm sure Robert Law's watching in Dundee, Scotland.
Oh, okay.
And we've got friends in Australia. We've got friends in Ophelia's probably watching in Normandy, France. So Marty's going to zoom in a little bit on this as you take us through some of the pieces and parts of this.
Well, let's do a 5-minute SSME 101.
There you go.
Let's start with the fuel system. The fuel comes in with the low pressure fuel turbo pump, and this is where we interface with the orbiter. Fuel comes from the external tank through the orbiter MPS system and interfaces here. Fuel comes in basically at the inlet. All you're seeing is the head pressure or the weight of the column of hydrogen to this point, which over time comes around.
Just showing you how detailed that is there.
And so it comes around through the low pressure duct, comes through these fuel flow meters, which I have here. I haven't painted them yet, but that's what those are. Comes into the high pressure fuel turbo pump that you talked about. High pressure fuel turbo pump actually turned at 37,000 RPM. It was pretty big. This actually stepped the pressure up from a couple hundred PSI coming out of the low pressure pump up to 6,000 PSI coming out of the high pressure fuel turbo pump. When it comes out of the high pressure fuel turbo pump, it comes and it's split into 3 coolant loops through this diffuser, we call it. The 3 coolant loops, the main one is the fuel actually comes around through the chamber coolant valve and actually feeds the preburners. And like I said, this is a fuel rich, so there's a lot more hydrogen in the preburners than there is oxygen for complete combustion, but we'll get back to that a little bit later. After it goes through the pump, it comes down and it actually cools the nozzle. If you can see these 3, we call these the steer horns. There are 3 of them around and they're built into 2, and the fuel comes down and comes up the nozzles. This nozzle is made of tubes, and I've kind of shown that in this model through these tubes. There are 1,080 tubes, and that cold
1,080 tubes.
1,080 tubes. It actually, the fuel turns into somewhat of a gas from a liquid, but it starts at the minus 450 degrees Fahrenheit, like I said, and it actually cools the nozzle. That's required because the main combustion chamber burns at 6,000 PSI and 3,000 degrees Fahrenheit. So any metals would not stand up to that. So the nozzle is cooled that way. Another coolant loop is a separate tap off, comes out of this diffuser and goes to the main combustion chamber. And that is shown right here through this line. And it has a separate coolant loop to cool the really hot area where the rubber meets the road in the rocket engine, right there at the main combustion chamber, right there at the throat. There's another coolant loop that is tapped off, and it turns the gas and it actually drives, and you can see this duct right here. This is what drives the fuel turbo pump. We tape a little bit of that hot gas that is warmed up, actually expands and provides us with a lot of energy. So we use that to spin the low pressure turbo pump. So at the end, the fuel comes in, and it is a lot of it is dumped into the preburners.
Is that a term, redactive? What am I thinking? Where you're harvesting?
Regenerative.
Regenerative.
Yeah,
Okay.
this is regenerative nozzle,
Okay.
and it actually the phase change does a lot of cooling. And so this is fuel rich. So let's go to the oxygen side.
What a beautiful model, though.
Yeah.
Yes, everybody's
So
enjoying this.
we have the
I'm
low
sure.
pressure, again, the low pressure LOX duct, or LOX pump.
It's up at the top, up
Yeah.
there where it enters. All right.
This low pressure LOX pump works at about 5,000 RPM. It doesn't work quite as hard, but
5,000 RPM is not working
well,
quite as
they
hard.
compared to the other pieces that we see. So it comes down to the low pressure duct, comes around, it comes past this pogo, and if we got a minute, we'll talk about this pogo device right here. And we'll talk about it now. This pogo device actually is an accumulator that absorbs and dampens any pressure spikes or variance that you get in the flow of oxygen. Oxygen is a very heavy liquid. If you hold up a gallon of water, for instance, you know, the gallon of water is going to be about $8 a gallon, 8 pounds a gallon. But oxygen is much heavier. So any spike through that is a water hammer kind of effect that comes through there. So this pogo absorbs all that. So you go into the high pressure oxidizer
the
turbo
pogo
pump.
you're talking about.
Yeah,
Kinda looks like it's kind of like a condenser then, huh?
Well, accumulator is a good word
Okay.
for it. It's actually an accumulator, and it absorbs any pressure variance. And if we have more time, that was an offspring of something we saw on the Apollo program. It really wasn't an issue with SSME because we didn't have such a tall stack, and we didn't have the liquid hammers or water. We call them water hammers, but it was oxygen, and it would come in and it would do some damage sometimes. So this is just absorb it and be like an accumulator. So this high pressure oxidizer turbo pump turned it over to 22,000 RPM. It is pumping a lot heavier liquid, and out of the high pressure oxidizer turbo pump, we had a couple tap offs. One tap off is it's tapped off, and this duct right here comes around and actually drives the low pressure oxidizer turbo pump. When it's
That
finished,
one right there, you're talking
yeah,
about.
when it's finished driving that pump, it actually gets back into the main flow again. There's another tap off the just before the main oxidizer valve, and this tap off is ducted back into the bottom of the high pressure oxidizer turbo pump. And there's another high pressure pump at the bottom here that runs on the same shaft as the main pump, but it pumps it increases the pressure to over 7,000 psi, and that oxidizer, and this is kind of important, this oxidizer then comes out of this duct after it's been boosted to a high pressure and comes up to these two areas to the preburner. And this is actually the oxidizer that feeds the preburners. Now, as we said earlier, the engine is a fuel rich, so you saw a lot of fuel being dumped into the preburners, but a very little bit of oxygen. And so when it's burnt, it reacts just like a mini rocket engine. It's not complete combustion because it uses all the oxygen in the combustion, but it has a lot of extra fuel in it. And so it turns that into a hot gas that's very fuel rich. So that fuel rich material, after it explodes and expands, it turns the turbines on these two high pressure pumps, and then that hot gas is then ducted out of that turbine through these crossover ducts into the main combustion chamber, and it's this hot gas that actually serves as the fuel in the main combustion chamber. So that's what makes it very efficient. It doesn't waste any fuel. Earlier versions of rocket engines, they had gas generators, and they would do the same kind of thing. They would tap a little bit of fuel, a little bit of oxygen off the side, and then spin the pump turbines. But then they would duck that overboard, and you're wasting a lot of energy. You're wasting some energy, but it was very simple, and it made things operable. This SSME decided to save all the energy from all of the propellants and burn it through a fuel-rich technique, and actually spin these pumps and serve as the fuel. Now that's the simplified version because there are tap-offs, there are the fuel and oxidizer are going all over the place, but that's basically the operation.
That is amazing. The harvesting, in my layman's term, is all this stuff. What are those right there?
Well, see, that's another.
These little white things right there.
Yeah.
Just curious.
So if anyone who is that familiar with it knows, these are the actuators, the thrust vector control actuators that actually steer the engine.
Oh,
I said earlier,
that's how it can move.
yeah. So not only is it throttleable, it's this engine is steerable.
Yes.
And when you attach this to the engine, you have these actuators, these thrust vector control actuators that would actually push and pull, and you could gimbal the engine in two planes, so you can basically
Up to like 11 degrees. Or
11
something
degrees.
Like this,
It
as
would-
the maximum I
yeah,
read.
and so you would push it, and all the three engines had this, so they would all gimbal in the same direction. And
That was one of my favorite parts of the liftoff, is when you saw the engines
Mm-hmm.
gimbal with all of your it's fueled up, being cooled down, and so forth.
Mm-hmm. And it's very smart.
They're going to be going now. They're gimbaling the engine.
When you know we're in the gimbal test, we're getting close.
Yeah.
And so that, yeah, but see, people who are true rocket scientists would understand that when this engine had the red GSC, when it's not installed, we never installed the TVC actuators on the GSC, and you never saw this. But I thought for my model, I wanted to have TVCs involved, just so you could see it.
Well, there's the power heads there. Kind of a close up of those.
Yeah, so you can see how, let's say you can see how the oxidizer is burnt a little bit in both preburners, in both this preburner and the other one.
Okay.
And that exhaust from the work it does to turn the turbines actually serves as a fuel in the main combustion chamber.
That is, what would Robert Goddard think of this engine?
I think he'd
we
be
love talking about Robert Goddard, Marty
Mm-hmm.
and I.
He would, I think, be very impressed. I think he'd be happy, and I think he'd be validated that he was a shy person, and I think he'd be validated that his work actually amounted to something, because he was a great proponent of liquid propellant. There was a lot of talk about, going to solid propellant a lot of times, which I like to refer to as fireworks.
Yeah, exactly.
But liquid propellant,
solid rocket boosters,
and when he saw,
hot bottle rockets.
yeah, if he saw that we were using hydrogen, which in his day was, just out of reach. In fact, hydrogen really wasn't in reach till just before the Space Shuttle Main Engines. It was just such a difficult fuel to use that several companies had trouble with it. Pratt Whitney was an expert in hydrogen pumping, and it turned out Rocketdyne was really good at it too.
Mm-hmm. There's another Carlton Bailey shot of liftoff there. I should have showed the sparklers going on. A layperson like me, until I came here to the museum, didn't understand that at T-minus 10 seconds, these sparklers are starting to go off there. And then the engines are ignited 6.6 seconds before
6.3.
6.3. Tell us about that pre-ignition of everything and why that was important.
Well, just
Before
before
the SSRBs go at zero, then there's no turning back.
liftoff, Ed, like Marty said, 6.6 seconds. The engines were started one at a time. We didn't want to, because there's so much liquid moving, you didn't want to start all three at the same time. You want to do one at a time to get the fluid going, so you wouldn't, put too much of a vacuum on the external tank in the MPS system. So they were stepped up. I think the 6.6, the next one was at another 1.2 seconds after that, and the third engine started 1.2 seconds after that one. So they stepped into it. But what happens is the fuel hits, just with the head pressure, hits the low pressure pumps, and the main fuel valve and main oxidizer valves are opened, and it kind of bootstraps itself. Now, if you take a look, and this is one of the problems we had developing the SSME, was the start sequence, because all these valves, you didn't want to flood the different areas with propellants. They had to come in a mixture ratio, and you wanted to kind of start slow and step it up. So actually the design of the final start sequence was a nightmare for a high pressure engine like this. So at the main fuel valve and main LOX valve, they would open. But just before that, we had a lot of purges. We didn't want to see a lot of hydrogen venting in the area. As you know, hydrogen is very explosive over a wide range of environmental conditions. So you wanted to not have an open air detonation of a gas bubble of hydrogen. So the system, they developed a system called the ROFI system. And I can't remember what ROFI stands for, but they were the
ROFI.
ROFI.
Okay.
And it was like,
Rapid oxygen firing.
Well, that I know. It's like
making stuff up.
They actually were
Ropey.
sparklers. What they did, they were igniters, that in case a small gas bubble had appeared, they would ignite in small amounts. You wouldn't allow a big explosion, but you would burn off the hydrogen in small amounts, and that's all they did.
The sparkler things
The
there.
sparklers,
It's like taking a cap off of a gas can and the gas vapors pool over there in the corner and you throw a match in there, poof, you could have a bad situation.
Yeah, and like I said, gaseous hydrogen is very explosive over a wide range, and you don't want a contained explosion of hydrogen. So those Rofies did that. Actually, we kind of touched over it, but in the pre-burners, we do have spark igniters, and they burn off. They turn on just at engine start, and they run for about 4.5 seconds, and they just get the pre-burner started. Once you start the fire, it's like lighting a candle. This thing will stay lit. But getting back to the start sequence, all these valves, they open and close, and they're very precise because you wanted the start sequence. Through experience, we came up with a sequence to make sure it started smoothly.
Electrical impulses open those valves?
Oh, yeah. They're actually hydraulic valves.
Some valves are pyrotechnics on bigger things, but I wouldn't imagine.
No. These engines, these are throttleable, so the valves open and close very precisely.
Right.
And that's why we had several on-pad or RSLS aborts, because if a valve didn't work precisely like it was supposed to, even though it was kind of keeping up, if it got outside the limits, we shut the engine down.
Huh. Our good friend Charlie Walker, astronaut, was on that first abort in there, and
so-
he said that was the ultimate pucker factor for him.
Yeah, we would like to apologize. I used to run into
Apologize, sir. I'll tell Charlie you apologize for that. That's
Charlie.
cool.
Well, I've had dinner with Charlie, and he mentioned that to me once.
Yeah. He'll be in town in a month, and we'll probably go out to dinner with him.
I don't know
We'll
if you
call up
remember us,
you
but
want to.
we would sit with him and his friend Jim Rose. We would sit and have dinner together.
Oh, wow.
And yeah,
Looks like Marty's got a question over there, a comment.
maybe someone in the audience knows what ROPI stands for.
More of a comment. You may want to mention that it's these, although I'm mentioning it, these are the three main engines that throttle down when you hit max Q. When you hear the word throttle down.
Yes. And but Marty, that's a good way perfectly to segue into this chart there of the 9 minute, basically about 8.5 minutes of the SSMEs going. And you can kind of briefly take us through that. And there's what's called a thrust bucket.
The thrust
that I've
bucket.
understood. So
Yeah. So this engine ran for 512 seconds. And another thing that we used to joke about in the firing room with John Plowden and Dan Hausman and Eric Garzi was the one true sign of a good rocket scientist was they could hold their breath for 512 seconds. So that's what you had to do, is hold your breath for that first 512 seconds. The thrust,
almost 10 minutes.
as you can see at the start, you see the thrust coming up very slowly on this chart. And so that's what we were talking about. It has to come up very slowly. You don't want to flood the areas with too much fuel, too much oxidizer. You want to step it up. And these pumps have to kickstart, as we showed earlier. Both low pressure pumps are fed and driven by output from the lower pumps. So it has to come up slowly. And then we get to 100% thrust. And at 100% thrust in the 6.6 seconds, we got to 100% thrust in about half that time. And when they came up to the full thrust, we would send a signal to the Space Shuttle Orbiter to say we're 100% thrust, we'll go for launch, and that the computer on board the orbiter made the decision go or no go at that time. And that's what gave the go to SRBs to ignite once these came up to full thrust. And so we would take off, we would do tower clear, and would run for some time. And then I guess after about a minute and 10 seconds or a minute and 20 seconds, because the aerodynamic forces on the vehicle, what we call max Q, and max Q is not so much, just not speed by itself and not just atmospheric pressure by itself, but the two kind of mixing together. When the speed of the orbiter got so great and you were still in kind of relatively low atmosphere, it would put the most stress on the vehicle. And that's what we called the max Q. So to get around max Q, to not have the vehicle shake apart or to have undue stress on it, we actually throttled this vehicle, these engines down. And that was done through these two valves here, the OPOV, oxidizer preburner oxidizer valve, and the oxidizer and the fuel preburner oxidizer valve, and they both are what throttles the engine down. They control the turbine speeds in the high pressure pumps. And so we would throttle down to 65%, and that would slow the vehicle down noticeably if you were on board the vehicle. And I think you had a friend.
Winston Scott, astronaut, said he talked about the thrust bucket, where you were inside the bucket, they said, because you're slowing down. And he said you could feel the vehicle slow down and then kick back up again.
Mm-hmm. But, even though this engine is a
But you're going 1,000 miles an hour at that point.
It's not like if you see pictures of what they saw on staging on things like the Apollo program.
Mm-hmm.
I mean, they were
Right.
really tougher. But this was most of the astronauts felt about 3 Gs. And when you're sitting back in your chair and you're feeling 3 Gs, and all of a sudden you only feel 1.5 Gs, you feel like, well, maybe I'm floating a little bit.
Uh-huh.
But then after we get to the max Q, and we'd get higher, but our speed would still be increasing, but we'd be higher out of the atmosphere. There wasn't so much air. There was not enough pressure. So we'd throttle back up. And, of course, those are some famous words you hear, go with throttle up. And so that's what that meant. We'd throttle these 3 engines back up to 100%, and they even go to 109%, depending on the mission, to give us some extra kick. And so that's what we called the thrust bucket. And then what we would do is we would just run these engines all out, and the astronauts in the vehicle would feel about a constant 3 Gs. Even after SRB separation, they'd just feel the 3 Gs. And then as we got close to orbit, we actually would play with the throttles, because we would get a signal from the orbiter to our main engine controller, which actually was the brains of the engine, which told it what to do, when to throttle, and what throttle. And it actually did all the other things, like controlled the throttling valves as a closed loop control. Mm-hmm. We would actually, if we kept driving this at 109%, the astronauts would exceed the 3 Gs. So we actually saw some throttling down just before orbit and just before shutdown, depending on the payload, the weight, the atmospheric conditions. We would throttle this to get us into orbit and shut down the engine at MECO.
Now, Kevin, explain to us how you can get more than 100%.
Well, what you do, it's easy. What you do is you rate the engine, you design the engine, design the parts, the wall thicknesses, the structural members, the flow rates around what our target was. Mm-hmm. And our target was about 375,000 pounds of thrust at sea level.
Okay.
Now, when you're at altitude, that increases, because you can get more thrust out of an engine at altitude. And so what we did was, during all the testing we did a lot of testing in this engines. We would test it to see, well, let's see if we can get it to go a little bit faster, a little bit more thrust. And we would do the math. We had to do a lot of analysis to make sure the wall thicknesses, the flow rates could handle it. Mm-hmm. And through not only mathematically, analytically verifying that we could go at a higher percentage, we actually did a lot of engine testing on the ground, where we pushed the engine to that. And after we satisfied the requirements to show analytically and demonstratively in a test stand we could go to 109%, we did that. And I think when we first started, I think we aimed at 104%. And then, people would ask the question, well, what if we went to 110%? And so we did all that analysis, and it was determined 109% was a sweet spot. And so we actually rated this engine at a higher thrust over time, but we still went off the original requirements at the 375,000 pounds of thrust.
Thank you. Perfectly explained to me. Now I understand that. That's you can get 109% out of an engine. I'm not sure you can out of a football player. Okay, they say give us 110% today, and that sort of thing. So, Marty, we've got a lot of people watching today. Why don't you read off a few of those names on our UCAC family microphone there, please?
Too many for me. Okay, we have. I put my glasses on.
I'm afraid there's going to be some of my Rocketdyne comrades who are
I
going
think
to point out.
Yeah, Iglesias Vicini, Tom Schultz, Nick Herrera, Lawrence Scarlett, Anna Joe, Dave Stange. These are names we know. Carlton Bailey, Tom Usiak, Cynthia Rossi, Gary Folsom, Robert McLennan, the Titusville Area Chamber of Commerce, Space Monkey, Doug Forrest, Gary Jarrell, Hazel Banks.
Say that last name again, Giroux?
Gary Jarrell.
Oh, Gary Jarrell.
Yeah, he's a Vidalia onion farmer in Georgia.
One of
Collins, Georgia. In fact.
one of Marty and I's old friends, avionics engineer for Rocketdyne, used to be Kelly Jarrell, so that's what.
Oh, okay.
Okay, you also have Carol Kavanaugh. I think I said Bill
Carol
Wyatt.
Kavanaugh.
Yeah, Carol Kavanaugh. Hello,
Thank you
Carol.
for watching, Carol.
Yeah, Larry Pushkar, Tom Celentano, Tony Achilles, and Neil 1030.
Tony Achilles, good to see you chiming in there. All lots of them are regulars that watch our video podcast.
Does any one of them know what ROFI stands for?
Anyone know what ROFI? ROFI.
I can't remember. Oh,
Tom Musiak's probably.
you know,
did
it's
some
radio outgoing fuel igniter. Radio outward.
That's what the sparklers were talking
radio
about.
outward
Radio
fuel igniter.
outward fuel igniters.
Firing igniters.
Firing igniters.
Yeah,
Okay.
so it came back to me. See what happens when you've been retired so long. It came
Well,
back.
we appreciate you all watching. You are doing an awesome job, Kevin, of explaining rocket engines and simplicity. He's got a beautiful 3D model that he's done. And when you look at the engine, there's a box on it that's the computer part. And Marty, you had something that's what you're part of it, right?
Yeah.
On the engines there. Just fascinating how what I call harvest their own energy to move the rotors and stuff like that. But we want to talk a little bit, Kevin, about this picture behind us here. Was taken at this testing a mature design, not just testing them in their infancy, but one of the success stories of the SSMEs is their ability that you constantly investigated issues, resolved anomalies. That's what this chart is all about here. Verify and increase the operational envelope. Malfunction testing to demonstrate redundancy, over test to demonstrate safety margins, and that was all done at this facility here. That you've been out there a few times, I imagine.
Oh yes, especially when you're assigned to Vandenberg, we didn't have any real hardware there, so I spent a big part of my early career at Stennis.
Stennis, outside of Huntsville, Alabama.
Well, actually further south, actually just outside of Slidell, Louisiana.
Yeah, right. Yeah, Slidell, Louisiana. Yeah, I'm wrong. Yeah, it's on I-10 near the Infinity Museum of Fred Hayes.
That's
is where
right.
you take your tour from. And I had a roommate from Slidell in college, Louisiana.
Slidell, Louisiana. We had to test a lot. One is to we called it green run because these engines were reusable. Each part had to be green run, which means accepted into the flight program by being actually tested on the test stand. So we had several of these engines, of these 46 engines I talked about, were constantly being tested, not for testing the engine, but verifying components, individual components. Each component on this engine, as it was brought into the inventory, had to pass 3 green runs. And so we did a lot of green run testing, which is part of that, all the seconds we put on it. We just talked about the requirements to test this to 109%. Well, part of that was what you had mentioned, limit testing, seeing how we can go above to spread the envelope of the engine. And then, of course, whenever there was a malfunction, we would try to recreate it on an engine at a test stand. Very controlled, and you could put special instrumentation on this to investigate any anomaly that you saw in the data. For instance, when a valve, we had a couple on-pad RSLS aborts. And what we do is we take that valve off that failed and we'd ship it to Stennis. They would put it on the engine currently in the stand and try to recreate it and know what caused the problem so we could solve it and never have it happen again. So, and again, just to keep the engine, to make sure we understood the engine. You have to understand that this engine was developed in the late 70s or late 60s. The contract was awarded in 71, and we were still using slide rules in those days.
Wow,
so,
yes.
through the engine testing, you got to know the engine intimately well and how things interacted and what key characteristics you saw, how they were, whether there's something to worry about or something not to worry about. So I think you had the number. How many seconds of test did this and flight did these engines have through this the whole program?
1,095 and 1,995,677 seconds, according to this chart here. Glad you asked, Kevin.
And that makes it the most tested engine out there.
Yeah, the hot fires. So you're saying that every SSME engine before it went on a space shuttle mission had 3 green run tests. So that's 9 minutes, over 9 minutes.
Well, what happened was to get an engine started, we would do just a short test to get it, just a couple seconds to get it to main stage, to make sure it got to main stage, and then we'd dry it and get it ready. And the next was a longer test, get it in the main stage and try to get some valve movement. And then the final approval for green run was running the engine at a full 512 seconds.
Wow. So before they were put in the aft of a shuttle.
Before.
And you dealt with OV-103 almost exclusively.
Well, in part of my career,
Discovery,
part of my career was that's all I did was follow.
Which was the workhorse for 39 missions on there. So, yeah, that chart, I know you can't read all that on there, but I broke it down that in the SSME start of its tests there at Stennis, they've got 18,261 minutes, which is 304 hours or 5 solid days of running an engine. That's just incredible for 9 minutes. That's really, and then that lends itself to this. What we have up there is the conclusions about testing. Testing is necessary even on a mature, well-understood production engine. Acceptance of testing sometimes reveals issues in new hardware. Some problems do not present themselves until late in production. When you're building 4 dozen engines, some design features, like mating of certain components, for example, can only be demonstrated during a hot fire. And some issues are vehicle driven or are related to flight operations that change outside the engine's program's control. So,
Can I ask you where you got those charts? Those are official charts.
Pratt Whitney,
Mm-hmm.
a Pratt Whitney. I can show you where that is. A woman and a man. Their analysis of the engines after the program there.
Mm-hmm.
So yeah, I found these really helpful. And then the lessons learned is a result of the relentless pursuit of improvement, and that's kind of like a Boeing, mantra there, I guess, huh?
Well, safety was number one, and I'm pleased to say that that the workforce out there was always focused on safety first.
Drive for understanding, and I love this: fix problems, don't manage the problems. Incorporate multiple changes. You had like 4 or 5 different block engines throughout the 30-year program of that. But yeah, fix problems, don't manage them, like some systems of the space shuttle were, which will go unnamed. They tried to manage some of the problems there, and it bit them. What kind of new technology? I mean, off the top, analytical tools, materials are key to the SSME success.
Well, modeling has always been very important because you can analytically try to determine what would happen if you change some characteristic or some measurement on the engine. You see what its effects are downstream. But like I said, there's always some room for improvement. I can tell you on the Space Shuttle Main Engine controller, the controller that runs this, when I first started the program, that controller weighed 208 pounds. It had 4K of memory on it.
4K, wow.
And it was highly reliable, but by the time technology is approved and incorporated into a human-rated space program, it's already obsolete technology. So, during the engine testing and during the evolution, the controller was stepped up several times. And one of the improvements they've done to separate this from an SSME to the RS-25 on the Artemis is the controller. They actually have a digital controller on there now. And I don't think it's not as robust, but it doesn't need to be because it's only going to fly once.
Mm-hmm.
But
There you go. Yeah.
so that shows you the evolution. So even though the outer mold line of this engine looks the same, there were constant improvements, tweaks, adjustments to it. There was a time when we used to make this high pressure fuel duct out of titanium. I think now they determined since it's going to Artemis, I think they just made that out of stainless steel now. One of the changes.
You mean since it's going to the bottom of the
Since
Atlantic
it's-
Ocean? And you
breaking my heart.
You hate thinking about
Yeah.
that. I mean, yeah, really. What do you feel about that? It's like, are these like your children, sort of thing, in a rocket engineer's world of
Well, one thing you'll find
Rocketdyne
when you
stuff?
talk to any of the Rocketdyners, it was a family of men and women who had extreme pride in their product, and it was their life for a long time, and it was the lives just about everybody. It was their life, and so it was a real camaraderie, and like I said, it was competitive, because like I said, just hanging around smart people all the time. It is very competitive, and it sorted out the good from the bad real
be
quick.
good competitive within
Oh, yeah.
the engineering of your clique there.
And people were recognized at the Rocketdyne for their intelligence or their ability to understand the engine and their hard work. And so there's a real pride in the profession on this engine, and it became our lives. And it is an engine to be proud of, like you said, all the statistics. And even now you can see, people point out, well, the engines are made cheaper. Elon Musk's engines are extremely reliable. But you have to remember, this was designed by slide rules. It was heavily managed by committee, and Elon enjoys, newer technology. So I really think that the folks who made the Merlin engine so incredibly reliable actually stand on the shoulders of people like Dick Carlson and Lee Solid and John Plowden and Gardsey and Hausman and the whole generation.
Kevin
of folks.
Hoshstrassoer there.
No.
Well, you're holding up the guys that are holding up the other guys.
That's exactly
there.
what.
Okay.
That's exactly what they'll tell you.
There got to be someone at the bottom of the pile, Kevin.
That was me.
Okay.
That was me.
There. We're way too humble. You have really done a great job, and I know our Stay Curious listeners have really enjoyed this hour. It's just breezed by here, Kevin. We certainly will have you back. Maybe we'll have you and Dan Hausman on together. And,
Well, I'll be quiet during that session.
will you? Well,
if I'm smart, I'll keep quiet.
Like Kevin's been emphasizing, there's a beautiful shot of the SSMEs working at the edge of space there. Like you said, they afforded you an opportunity to play around with them a little bit, huh? To see what maximum you could get out of them there.
If you talk to any astronauts, they'll say that was the smoothest ride that ever. Make a point to ask them when you see them, because once you separate the SRBs, this was one smooth ride.
Oh, it's like a sports car, most of them say. That's the fuel tank, by the way, taken up there with them. But these SSMEs, designed by slide rules in the 1960s, 50 years later, are strapped on to the bottom of another rocket tube, the Space Launch System, that, they're going to ditch them in the ocean. All that beautiful manicuring over 3 decades of these engines. I think I find that very interesting. But they can tell exactly what shuttle missions all these engines of Artemis 1 went on. There shows you some of them there, how it was configured. And the rocket launched by Mark Usiak. Mark, thank you for sharing your photography with us. 2 brothers, Tom and Mark Usiak, photographed over 60 of your shuttle launches. They live in Lancaster, Pennsylvania, and become great friends of our museum there. But this rocket engine's the 50-year technology, really. I mean, with, of course, the modern upgrades, like you said, a digital computer and so forth.
It's still basically the same engine, same technology, and a lot of smart people with slide rules figuring out the combustion ratio and the flows and the thermodynamics required to get this effective.
And that's what you have 50 years later when you have pride in your craft of what you do, which I love. The competition, you say, was among your engineers. It reminds me of the news business that I was in, because some of my favorite memories in my working career are in a couple newspaper bullpens where we were all alpha dog men and women wanting to get that our story on the front page or type of thing, and it instilled in me particularly a positive competitiveness to do my best. at all times and exceed expectations.
In a family atmosphere, that's what it was.
In a family atmosphere.
And with families, you get some of this,
Uh-huh.
but they're in all families. But it was very, very rewarding to work at Rocketdyne and the Rocketdyne people.
Well, Marty's Grummies were a lot like that, I think. I don't know how competitive you all were, but you all had pride in your craft, too. Marty, you got a question there.
You've got a question from Dave Stange. Kevin, how do you feel about these engines now ending up in the ocean?
It breaks my heart as an individual. I have to go with the nation's directive to go to this way, and if it gets into a whole other topic, but the history of that decision being made, the NASA decided instead of going to a new development, since we have a million seconds on this engine, it was cheaper, smarter, faster to go ahead and use something that they knew and modified the MPS system of a rocket to go with it. It also broke our hearts. For a long time, we always had Russian engines on site. They didn't launch space shuttles, but they launched expendables. And having Russian engines on site always rubbed me the wrong way too, because this is, the knowledge of rockets is something that we want to keep, U.S. leadership in. And when you decide to buy cheap Russian rockets that were very reliable, the RD-180 was a very reliable engine, and boy, was it cheap. They could buy a whole slew of them for just one of these. Of course, that was expendable. And so it broke my heart to see Russian engines being launched in the United States, but it still breaks my heart to see these go into the ocean. But that's the national directive, and we'll go with it.
Well, there'll be a few of them left over, I think. You said there was, we're down to 14 left, right?
And there was already some. I think all the museums that really would honor having them already have them, so not too many of them need to be saved.
Yeah. Well, Marty, we've certainly enjoyed this. Do you have any questions for Kevin, one of your working colleagues there? So we got Robert Law. I told you he'd be up enjoying his evening cocktail in Dundee, Scotland. And Maurice Krozowski, he is in Europe somewhere. I forget. I've looked that up, and I'll look that up again. But we've got a lot of people that enjoyed this conversation. Kevin, you did an outstanding job of taking some rocket science stuff and very easy to understand. Is there something we didn't ask you that you'd like to share with our viewers today?
No, the only thing I guess when we talk, the next time we talk, we're going to SSME 501, more details about how engines work and combustion ratios and the physics of it.
Sure, we'd be happy to do that.
No, I've got
we'd be happy to do that. You're always welcome to come back here. We look forward to seeing you
Whatever.
again. You've got some other models. You've got the with the air spike, they called it.
I've got an F1, 1 to 12 scale and 1 to 18 scale. I've got a linear aerospike and the annual aerospike. And just for fun, I designed and 3D printed a BE4 engine.
BE4 is the
Bezos engine.
engine for New Glenn.
For New Glenn, and also being used on the ULA Vulcan rocket.
Okay. All right. Well, I loved his little diagram there. We can do that a couple times there with these engines there.
I would like to add, I really admire the work that you folks do here at the American Space Museum and the dedication of all the volunteers and the people who work here. I really admire that.
Well, thank you very much. How do you find our artifacts in our humble little
It
museum?
brings back a lot of happy memories sitting at a console.
The C-12 there that you
it's
mentioned, right?
Sitting with Marty,
Fueling
third
the
shift,
station.
waiting, just watching the controller, pressure and temperature. 3 days out from launch, that was my job.
Yeah.
Sitting there with Marty and trying with George Page in his office, making sure that no one ate or read newspapers in the fire room. The good old days.
He's the first launch director for the
Great guy.
shuttle, also an Apollo icon in there. There's a lot of characters in there and unique personalities that checker our wonderful American space program. And Kevin, we're so happy that you're here to share.
Thank you very much.
Share it with us. No, thank you. This was a very interesting talk. Dan Hausman, you got your work cut out for you when we invite you back here. But no, we'll look at your 3D models there in more detail there. But Kevin, thank you for a wonderful Stay Curious program. Marty, a flawless job on your end there. I know we had a lot of people watching today, and they can watch it on YouTube. Tell your friends and family that the American Space Museum brings to you people that we call national treasures, like Kevin here, Kevin Hoshstrassoer and Marty Winkle, worked on these programs intimately. They were just one of thousands of people involved that made it work, but nonetheless, we're pleased that they could share their story on Stay Curious today. Thank you again. We hope to have you back, Kevin. Until then, I'm Mark Marquette saying tomorrow's Wednesday, Hump Day. I'm going to talk about the planet Venus that's going to be disappearing in our western sky. And if you look at it through binoculars, it looks like a crescent moon. And it's at its brightest phase. We're going to talk about that. The sun acting up, and we're going to give you some more auction items. As Saturday is another important auction for the American Space Museum. Believe it, you better believe it, that we keep our doors open with the money from these auctions. So we'll be sharing with you some of the 370 items that Mr. Chuck Jeffrey is going to be auctioning off as our collections manager, or collections analyst here at our American Space Museum. So until then, Kevin, thanks again. Marty, thank you. I am Mark Marquette saying we can't wait to see you tomorrow to bridge the space between us.